Welcome to Pre-Calculus. Today we will investigate analyzing logarithmic functions. We'll look for domain, range, and behavior. And then we want to write an equation for each function from the graph and from the transformation data that's given. We'll take a look at two examples. Here's our first one. So here I've got a logarithmic curve that's been transformed from the log base 2 parent function. So I got some information. It's been shifted left 2, down 2, and then it's got a vertical stretch by a factor of 4. As I look at the graph and think about writing domain and range, I'll start with domain, which is a description of the x values of a function. I've got to mind the fact that there is going to be a vertical asymptote. And so I see definitely that this vertical asymptote is going through -2. Definitely I see that on the graph. I also see it here in the transformation data. It's been shifted to left, so the parent function is going to have the y-axis as its vertical asymptote. That helps me to write the domain. So when I think about the left extreme of this graph, I can highlight the arrow that's mostly tending towards a negative direction down. But it's not ever crossing this vertical asymptote at -2. So that left side for the domain is going to be restricted at -2 by the vertical asymptote. So that's less than x. And then less than on the far right side, there's no restriction. I see that right side is traveling forever towards positive infinity in the x direction. So one major difference between domain and range for a logarithmic function is that its domain, unlike exponential functions, is not all real numbers. The domain is going to be restricted by an asymptote. So I'm going to write that interval notation parentheses -2 comma infinity parentheses. For my range, I'm trying to describe the y values. And this is going to be more like the domain of an exponential function. Remember, logs and exponentials are inverses. So if an exponential function has a domain of all real numbers, the range of a logarithmic function should be all real numbers. So I'll go ahead and write it -infinity less than y less than infinity. We just need to confirm it. So on the graph, I see the lower part of the graph is tending towards -infinity. The upper part of the graph is headed in an unbounded direction up. So definitely my range is going to be from -infinity to positive infinity, or in words, all real numbers. Well, that wraps up domain and range for this function. For the end behavior, I'm going to look to the range to help me describe the end behavior. Really, it's a matter of describing as x heads to the far left, what's happening to the y values, as x heads to the far right, what's happening to the y value. And really, I'm putting the two domain and range together. I'm going to say that the limit as x approaches, so I'm looking at that far left side, that's -2. That's the vertical asymptote. So as the function gets close to the vertical asymptote, it's going to equal, in my range, I see the description is -infinity. And I can see that at that lower part of the graph. So that takes care of the extreme left side. The extreme right side is not limited. So remember, on my domain, that right side was headed out towards infinity. So the limit as x heads towards infinity equals, my range value there is positive infinity. And I can see that here on the upper part of the graph where it is headed to the right unrestrictedly. At this point, I want to now take my information that I got about the transformation of this function, and I want to write an equation. So the way I want to do it is by setting up a template. So it's going to be f of x, and I've got to fill in some parameters. So there's going to be an a number out front that's going to either stretch or compress, possibly reflect the graph. times the logarithm. Now I'm told the parent function here is log base 2. So I'm going to go ahead and fill in that base 2 of, in this case, x minus b. And that number minus b, that's my left-right translation. And then on the outside, plus c. And remember that plus c determines the up-down shift. So really, I just need to fill in for the a, the b, and the c. And that's the information that I've got here. So if I start with this a, and I'm looking for either a vertical stretch or a compression, I'm told the dilation here is a vertical stretch by a factor of 4. So that's what I need to input there, is that this is a 4. And then it's been translated 2 to the left. So I need to put the 2 by the x. That's where the left-right translation goes. But remember, the sign is opposite. So if I've translated to the left, the sign needs to be plus. And then on the far outside, I see that the graph has been shifted down 2 down in my data. So I'll put the 2, but remember that one on the outside, we actually follow the sign. So I'm going to make that minus. And that gives me a good equation for this function. F of x equals 4 times log base 2 of x plus 2 minus 2. And just so that we can kind of check our prediction there with the equation, I want to head to Desmos and graph this. Again, it's just a quick check. I'm going to type in the function we wrote. So f of x equals 4 times log base 2 of x plus 2, and then on the outside minus 2. And that looks virtually identical to the graph we're seeing on our note screen. So I'm going to head back to the note screen. Again, Desmos is useful as a check for that. Well, let's take a look at a second example. So here I've got a function that's been reflected several times. So it's got some other transformations, but the main difference between this and the first function is this one's been reflected at least twice. But let's find the domain, range, and end behavior first. So domain for this graph, again, is describing x. And because of the reflection here, I see that the graph on the far left is unrestricted. On the left, it's headed towards negative infinity. Where it is restricted is on the right side. So as I write domain, negative infinity less than x less than, I'm looking for the vertical asymptote. Well, that appears to be right here at the y-axis. So the number I'm looking for left to right is going to be 0. So in interval notation, from parentheses negative infinity comma 0, and then I'm going to use a parentheses because, again, an asymptote's a feature that the graph does not touch or cross. Then I can describe the range of the function. And as we've seen with our previous function, our expectation is that this should be from negative infinity to positive infinity. And I see here on my graph, definitely on the lower side of things, it is headed down. It's not mostly headed down, it's mostly headed left, but it is going to decrease forever. The right side, I see the graph kind of disappear here, but that's just the way it's being drawn on the plane. It's continuing forever. In fact, I could extend it upward. And from that view, we're definitely seeing that this function is headed towards positive infinity. And that confirms our initial guess that this was all real numbers for range. So I'll write that in 3 ways: inequality notation, interval notation, and in words, all real numbers. For the analysis, our last task is to describe the end behavior of the graph. In end behavior, again, to reiterate, what's end behavior talking about? It's describing what's happening to y as the graph heads towards the far left and the far right. So again, we use domain and range to help. So I'm going to use that left side of the domain and the range. So the limit as x approaches negative infinity equals negative infinity. And we can see that on that left side of the graph. As it's headed to the left, it is decreasing forever. The right side, also I can use the domain and the range to compose that limit statement. The limit as x approaches, so it's not going to positive infinity, it's going towards the asymptote at 0. And as we saw here in our range statement, the function is headed towards infinity. It's rising up without bound as it gets closer and closer to 0. All right, so that completes our analysis. Last thing for us is to use this transformation data to write our function. So here's, let's call this one g of x. So again, I'm going to put an a times the logarithm. Here I'm told that it's just log x. Remember, that's log base 10. So you can write it or you can omit it. Typically, it's suppressed. Of parentheses. Now, here's a difference. Anytime I have a reflection across the y-axis, I need to include a coefficient in front of my x. So bx minus c plus d. And in fact, I need to switch that. Plus c minus d. There we go. In fact, I think, let me switch back. Minus c plus d. So again, I just need to fit in the information I've got. So I only have one translation. It's 2 down. So when I'm deciding between the c and the d, the up-down translation control is outside here on the d. And it follows the sign. So I'm going to make it minus, and then I'm going to plug in that number 2. So what I notice is there is no left-right translation. So I'm going to get rid of the minus c there. So then I just need to decide what this a is. So it's a vertical stretch by a factor of 4, I'm told in the data. So that's going to be controlled by that multiplier out front. And then the last thing I need to account for is the fact that I've got 2 reflections. The one across the x-axis is going to be controlled by this sign of the a, the 4. I'm going to put a negative that will reflect it over the x-axis. But I've also got a reflection across the y-axis, and that is a negative on the x. And that completes it for us. Our function here should be g of x equals negative 4 log base 10 of negative x minus 2. Again, the proof is in the graph. So I'm going to head to Desmos. I got this view of the graph kind of in my mind's eye, and I just want to check it by graphing it. So we'll type in our function like we wrote, g of x equals negative 4 log. I can put the base 10 of negative x and then shifted down 2. And that gives us a very identical version of the graph as the one that we're seeing in our notes. Well, thank you for joining for this investigation of analyzing logarithmic functions and writing their equations from transformation data. See you soon.